Alright, let's blaze through units 2 and 3. Let's try to do it. So, chemistry. Okay. Fill in the blanks, highlight with the correct words for the sentences. I just deleted the stuff. Okay, so A is pointing to this guy right here with the negative charge. That is an electron. Electrons are outside of the nucleus. They have a negative charge. B here pointing to the one with nothing in it. That is a neutron. Neutrons are neutrally charged. They are inside the nucleus and they have a neutral charge. C is pointing to a proton. You can see the little plus. It is inside the nucleus and it has a positive charge. Using your periodic table, tell me the atomic number for aluminum. All you have to do is look at a periodic table, find aluminum. Here, number 13, this number at the top, the smaller number, that's the atomic number. And that is the atomic number for aluminum. Easy enough. Find the atomic mass for oxygen, rounded correctly. Here's oxygen, 15.999. We're rounding that to 16. Boom. Tell me how many protons are in K, which is also known as potassium. Right here. What's it asking for again? How many protons? Protons and atomic number are the same number. So if the atomic number is 19, it has 19 protons. Potassium has 19 protons, excuse me. So how many neutrons are in an atom of krypton? This one you have to do some math for. Here's krypton. We have our atomic mass, which we can round this up to 84, and we have our atomic number, which is 36. Electrons are the only particles that don't have mass. Neutrons and protons do. So if we have our atomic mass, which is our protons and neutrons added together, and we have our atomic number, which tells us the amount of protons, we can just subtract 36 from 84 and get our number of neutrons. So 84 minus 36 comes out to 48. That's how many neutrons we have. How many electrons are in a neutral sodium atom? If we look at sodium, has 11 protons normally. If it's neutral, it's got to have the same number of positive and negative charges. So if it has 11 positively charged protons, we need 11 negatively charged electrons to balance that out. So it's got 11. How many neutrons are in an atom that has an atomic mass of 24 and an atomic number of 11? So if we're trying to find neutrons, we take our atomic mass, we subtract our atomic number. 24 minus 11 is 13. What charge will be formed by lithium? If we look at lithium here, we got two options. When atoms are forming charges, they are trying to form a full shell of valence electrons, usually. So there's two ways that we can do that. It has one right now because it's in column 1. Lithium has a 1 valence electron. We can either take that 1 valence electron away and there's a full shell underneath, or we can add 7. 1, 2, 3, 4, 5, 6, 7. Atoms always want to do the least amount of work possible. So it would rather just lose 1 electron than have to gain 7 electrons. So lithium loses 1 electron. When you are losing an electron, you are losing a negative charge. So that means that its charge becomes positive 1. It is losing a negative electron and becomes positive 1. What charge will be formed by sulfur? Sulfur is right here. It can either gain 2 electrons or it can take away 6. Adding 2 is going to be a lot easier. Sulfur likes to gain 2 electrons. Gaining 2 negative charges gives you a charge of negative 2. What is the atomic number of an atom with 12 protons, 12 electrons, 14 neutrons? There's a lot of excess information here. Atomic number and number of protons is always the same. Always. So if there's 12 protons, the atomic number is 12. What is the atomic mass of an atom with 5 protons, 5 electrons, and 6 neutrons? That would be 11. We are doing 5 protons plus 6 neutrons. That is 11. Electrons here. Did I say electrons there? 5 protons plus 6 neutrons is 11. We are leaving out the electrons because electrons don't have mass. Drawing a Bohr model for chlorine. So first let's look here. Chlorine, where are we at? 17. Okay. So if there's 17 protons, we're going to fill it in with 17 electrons as well. This is a neutral atom of chlorine. When you're drawing Bohr models, you have to always fill in from inside to out, and you have to know how many electrons go in each shell. So the first shell can only hold 2 electrons total. There's my 1, there's my 2. Okay, so there's 17 total. We just drew 2, so we have 15 more. Every shell besides the first one can hold up to 8, so we go 1, 2, 3, 4, 5, 6, 7, 8. Now we have 10 total drawn. Chlorine's got 17 electrons, so now we have 7 left over. 1, 2, 3, 4, 5, 6, 7. There's our Bohr model for chlorine. Lewis dot structure. It is like a Bohr model except easier because you only have to care about the valence electrons. And remember, there's a shortcut. when you're looking at the periodic table, if it's in this column, column 1 has 1 valence electron, column 2 has 2 valence electrons. We skip over this big middle section. Column 13 has 3, 14 has 4, 15 has 5, 16 has 6, 17 has 7, and then these noble gases have a full 8 shell of valence electrons. So, sodium, where's sodium at? It is in this first column right here. We know it has 1 valence electron. Wow, that was so easy. Okay. How many valence electrons does phosphorus have? Let's look. Where is phosphorus? Right here. Let's count the columns. 1, 2, 3, 4, 5. It's got 5 valence electrons. How many does magnesium have? Let's count. 1, 2. It's got 2 valence electrons. Calcium is more likely to lose electrons, while chlorine is more likely to gain electrons. How did I know that? Well, here's calcium. It can either lose 1, 2, or it can gain 1, 2, 3, 4, 5, 6. 2 is going to be easier. It's going to lose 2. It's going to lose electrons, form that positive 2 charge, whereas chlorine right here has the option of either gaining 1 electron to get a full shell, or losing 7. Gaining 1 is a lot easier, so chlorine would rather gain electrons. Why do noble gases like neon, argon, and krypton not want to gain or lose electrons? Because they have a full valence shell. That's why they're called noble gases. They don't need to do anything. They have a full 8. They're unreactive, because why would they want to give up or take electrons when they're in a perfect spot? They're not reactive. They don't want to exchange electrons. They're in a good spot. Explain the difference between ionic and covalent bonds. Long story short, ionic bonds, electrons are donated and accepted. In covalent bonds, they are shared. So, yeah, I mean, it's pretty much as simple as that. Like, in ionic bonds, someone really wants to give up their electrons and someone wants to take it. So it's pretty much just like, here, take it. I don't want any more. You can make good use of it. Whereas with covalent bonds, they both kind of need the electrons. So they both got a hand on it and they're sharing it. As we go down and to the left on the periodic table, what happens to the atomic radius? So as we go down and to the left, as we get into this corner, the atoms are getting very big, whereas here they're getting very small. You might think that they would get big as you go up every single number, but that's not the case. When you're on this side of the periodic table, your electrons are very close to your nucleus and they are being attracted to the nucleus very strongly, whereas out here, because there's so many electrons that are shielding it, it makes them kind of expand out. That's just my short explanation. And obviously, as we start adding more and more and more protons, neutrons, and electrons, the atoms are getting bigger the farther you go down. As we go up and to the right, what happens to electronegativity? It gets greater. Fluorine in this corner, in this upper right corner, is the most electronegative element. That just means that they like taking electrons. So as you get up into this corner, things like taking electrons more, and as you get to this corner, they like giving up their electrons more. As we go left to right on the periodic table, what happens to metallic character? Things become less metallic. On this side, they're very metallic. You might not think of sodium as a metal, but when it's not table salt, that's sodium chloride. When it's actual sodium metal, it is a silver-looking metal. All of these are silver-looking metals. These are all metals as well. Some of these even are metals, but then as you start getting here, it's questionable whether it's a metal. And then here, these are not metals at all. Oops. Okay. Cool. Let's get into the universe then. Labeling the parts of the wave. This is just things that you need to know. Wavelength is the distance from crest to crest or from trough to trough. Our crests being the top of the waves, our troughs being the bottom points of the waves. Amplitude is the distance from the middle of the wave, the equilibrium point, to either the crest or the trough. So it could be from here to here. It could be from here to here. This distance or this distance. It is not the distance from crest to trough. That is 2 of the amplitude. Amplitude is from this middle line, this equilibrium point, down to either the trough or the crest. That's the amplitude. Okay. What are the 2 types of waves? Transverse and longitudinal. I drew pictures of both of them here. Here is our longitudinal wave, our compressional wave. The compression is where the lines or dots or whatever are compressed. The rarefaction is the more spread out part. Which of these statements is false? Only electromagnetic waves do not require a medium. That is true. Electromagnetic waves are not mechanical waves, so they don't require medium, but all other waves do require medium. B, waves transfer energy but not matter. That's also true. X-rays are an example of a mechanical wave. False. X-rays are an electromagnetic wave. They are not mechanical. D, sound waves cannot be heard in space because sound waves are mechanical waves. That is true. Yes, we can't see sound waves, but sound waves are still mechanical. We know this because they need a medium to travel through. They need air, water, this desk I'm banging on right now. You cannot hear if the sound cannot travel through a medium. So, that is true. The false one is that X-rays are an example of a mechanical wave. Here are my 3 beautiful waves that I drew. Which one has the highest amplitude? B. It's just basically like, what is the tallest looking wave? That is the one with the highest amplitude. That is B. Which one has the lowest frequency? That would be C. Notably, C also has the longest wavelength. I jumped ahead a little bit. C has the lowest frequency and the longest wavelength. Which 2 waves have the same frequency? That would be A and B. Even though A is a shorter wave, it has a lower amplitude. They both have the same frequency. They have the same amount of waves per second, per minute, per hour, right? Because we see 1, 2, 3 wavelengths here, 1, 2, 3 wavelengths there. They just look a little different because B has a higher amplitude, but it's the same frequency. Look at waves B and C. If one is a microwave and one is a UV wave, which one's which? If you wanted to look up an electromagnetic spectrum, you could. You could see that UV rays are higher frequency than microwaves. So because B has a higher frequency than C, I would say that B would be the UV wave, C would be the microwave. And how many wavelengths long is A? We already counted. We're going from crest to crest 1, crest to crest 2, crest to crest 3. That is 3 wavelengths. Wave equation questions. This is another plug and chug very similar to the F equals ma equation. So we have our V equals frequency times lambda. That's what this letter is, lambda. It represents wavelength. So we have a wave with a frequency of 3 hertz and a wavelength of 2 meters. What is our velocity? We are solving for V, so we are just doing F times lambda, so that is 3 times 2 is 6. I hope you know that. If you have a wave with a frequency of 2 hertz and a velocity of 4 meters per second, what's your wavelength? We are solving for a lambda, which means we must divide both sides by F. So we have V over F is equal to lambda. We take our velocity of 4 divided by F, our frequency. 4 divided by 2 is just 2. Our wavelength is 2 meters. If you have a wave with a wavelength of 3 meters and a velocity of 9 meters per second, what's your frequency? Again, we are dividing both sides by the wavelength this time because we're trying to solve for our frequency. F equals V over lambda. We have our V of 9 over our wavelength lambda of 3. 9 divided by 3 is 3 hertz. That is the unit for frequency. Your friend asks you, how did the universe come into existence? Write a paragraph explanation, use the words Big Bang, redshift, maybe Doppler effect, cosmic microwave background radiation. Okay, so, sorry about that. Yeah, so I have about 2 minutes to kind of talk about this. So, I would really hope that you guys would look back at your Big Bang rough draft papers to get a good idea about this, but in short, we know that the Big Bang happened because redshift is what we see when we're observing the Doppler effect in terms of light. So, if we are seeing light coming from distant planets, galaxies, suns, whatever, and it looks more red than we would expect when we are looking for certain markers in its spectrum, we expect them to be in a certain place. Now, what on earth is this? That's my phone reminding me to record these videos. So when we see certain things and we expect them to be in a certain place on the spectrum, but they are shifted more towards the red, that means that they are moving away from us. That those waves coming from the light are being kind of lengthened out. Longer wavelengths of light look redder. Shorter wavelengths of light look bluer. So if it's coming towards us and the waves are getting more squished together, frequency is higher, we'd see blue shift, but instead we see red shift, which means that things are moving away from us. They are moving away from us faster than the speed of light. So it is shifting to look more red than it should. And then also cosmic microwave background radiation is kind of like that leftover microwave background radiation that was detected by those, I can't remember off the top of my head, but hopefully you guys would know from your paper. But scientists, I believe they were looking into space, right? And they ended up discovering that there was a bunch of microwave in the background when they were searching for other waves, and they thought that it was a miscalibration of their instrument, but it turns out that there are just microwaves around us all the time, constantly kind of echoing throughout all of space, and that's sort of like the leftover energy from the Big Bang happening billions of years ago, which started as, very hot and very bright, and it has sort of just calmed down into these microwaves over the course of time. Yeah. You should do more reading and more research on that, though, if you are having a hard time remembering the logic.